Hi everyone, I'm going to go ahead and do your notes for electron configuration on this video so that you can review it at home, and also for the A side. I know that we didn't get to go through this and you need to kind of be a little bit ahead before tomorrow's class. So I have this on page 28, yours might be different. I know that some pages might have been skipped because, for example, the quantum model notes, for me, it took 2 pages, so I just skipped a page and went to my next right-hand side, and I'm leaving this left-hand side, which for me is 27, blank for this homework assignment. Okay, so again, if your number is different, don't worry about it, just make sure it's on the right-hand side and that you have a left-hand side ready for that assignment on electron configuration. Alright, so what is electron configuration? This is basically a way that we just show the arrangement of the electrons in the atom. And there's several rules we're going to use to figure out how these electrons decide where to go in the orbitals. And the first one is that electrons fill the lowest energy orbital first, and then they go into higher energy orbitals after that. Now notice that I said orbitals, not necessarily energy levels. If you get this sheet out, you'll see going from bottom to top the orbitals from lowest energy to highest energy. And at first it does follow with energy level. So for example, the 1s is lower energy than the 2s, and then the 2p comes next, then the 3s, then the 3p. But then notice here we have 4s, 4p, and then 3d. So once we get to the d and the f orbitals, it actually no longer corresponds to the energy level. So keep this handy as we go through this, because it'll make a little bit more sense as we're going through it if you keep this around. The rules for following this is called Aufbau's principle. So we follow Aufbau's principle, and this is also in your book of figure 3.1 in this chapter. This is all chapter 4 also, in case you haven't been following along. Okay, rule number 2 is Pauli's exclusion principle. And this says that no 2 electrons can have the same 4 quantum numbers. In particular, what we're talking about is m sub L, which is the spin number. So as we saw in one example in today's warm-up, 2 electrons can have the same first 3 quantum numbers, but the 4th one, which is the spin, has to be different because they might be in the exact same orbital, but one has to have a 1/2 spin, a negative 1/2 spin, and the other one has to have a positive 1/2 spin. Okay. And then Hund's rule is rule number 3 that we're looking at, and that says that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. This is going to come into play when I show you the orbital notation. And also, all electrons in a singly occupied orbital must have the same spin. So when they're not paired up and they're in different orbitals, they're all spinning in the same direction. And we'll show you that in just a second. The first type of notation is orbital notation. And this is when we have just a line or maybe a circle, kind of like we have in these examples, representing an orbital. So when we take hydrogen, hydrogen only has 1 electron, and that 1 electron has to first fill the very first energy orbital 1s. So 1 electron can go in that orbital. We just draw it as a line or a circle, and we put 1 arrow showing that's all that hydrogen has. And then as we get to bigger elements, we have to figure out where their electrons go. So for helium, it has 2 electrons. Those electrons are going to fill in the first orbital, 1s. And remember, each orbital can only hold 2 electrons. So the first 2, the only 2 electrons in helium are going to go in the 1s orbital. If we do one like carbon, we start off by filling out 1, 2 in the 1s orbital, and then the next 2 fill in the 2s orbital. And so on and so forth. The more electrons you have, the more that you fill in 2 by 2 each of these circles. Now this can get kind of long to write out, so then we also have what's called electron configuration. And I'll show you the example of fluorine. So fluorine has 9 electrons. Let me cover that up for just a second. So rather than write out all of the circles or blanks to put in the arrows, we can also use this chart again and just see where would those 9 electrons fall. So in the first orbital, 1s, we put a 2 on the top denoting 2 electrons can go in there. In the second one, 2s2, the next 2 electrons can go in the 2s orbital, so we would put 2s2. And then we have 5 electrons left. So we would say those are going to go to the third highest energy level, which is 2p, and we would say 2p5, those last 5 electrons on there. But I put this on here to show you what this would look like if we were doing orbital notation. So we would start off by saying, okay, we have 3 possible orbitals in the 2p sublevel, and we have 5 electrons that can go in there. 1, 2, 3 electrons would fill in by themselves, and then the next 2 would find a pair. Okay, so this is an example of Pauli's exclusion principle and Hund's rule. Everything has to have at least 1 first before next 2 fill in. And once there is a pair in one orbital, like here and here, each one, we put the arrows going in different directions to show that each pair in the orbital has different spins. Now, once we get to really big atoms, it's going to seem a little bit difficult to write out the entire configuration from 1s and beyond, so we do what's called noble gas configuration. And I'm doing an example here of sodium. So if we look on our periodic table, sodium is number 11, and we know that sodium is going to look just like neon, which has 10 electrons. Here's our neon, plus 1 more electron. So we can say sodium is like neon, but then after those 10 electrons, that 1 extra electron has to go into the next highest energy orbital. So for neon, the electrons would have gone 2, 4, 6, 8, 10. They would have filled up to the 2p. So then the 1 more that sodium has goes into the 3s. So we would write it, sodium is neon in brackets, and then 3s, 1. And you can do that for pretty much any element. Now, there are some exceptions to these rules where they don't actually follow Aufbau's principle. And there's 4 that I'd like you to have memorized. And these are chromium, copper, silver, and gold. If you notice here, for example, with chromium, here it is, there's 24 electrons. And you would think that here's a 4s orbital, 2 electrons would fill this before they would go into the 3d orbital, which is less energy. But what actually ends up happening is that it's more stable for each of these d's to have 1 electron, even if it meant that this s also only has 1 electron, rather than have a pair here and then have an empty 3d orbital. So in the case of chromium and in the case of copper, instead of having a full s before we go on to 3d, the 3ds are either completely filled in the case of copper, or there's 1 per orbital in the d's. Silver and gold are similar. Their first s orbital after their noble gas, instead of having 2, actually only has 1, in order to have the their D, the 5D and the 4D, have a complete D sublevel. And there's not really a really great explanation for this, except that it just ends up being more stable that way. There are other exceptions, and you can see these in the back of your textbook. Let me show you. If you look at any one element, it shows you the noble gas configuration, and especially in the transition metals, you might find a lot of exceptions to these, but those are the 4 that I definitely want you to know. And for everything else, following these rules, you should be able to write out the configuration. We will go over this a little bit more tomorrow in class, and do some more examples. Please complete this page, just the front, for homework. And I think that's it. All right, thank you.